Hey everyone, welcome to a new tutorial. This one we talk how to create a particle system using the GL3 package from scratch. So we will kind of go through everything that is needed to work this out using the new package, which could be not so intuitive. So we will go through all the steps. Let's take first a look at this. So as you can see, I have 1 million particles, which is extremely good. I could never achieve this kind of level before using GGen, but also using GPU particle systems before. Somehow I could never go to 1 million particles. And I think this is now I can do this because this is the because the new GL3 package is much more efficient. We can actually go as much up to 5 million particles. Okay, so this is now 20 million particles, and I'm at 50 frames per second, which is kind of amazing, I have to say. Let's go full screen with that. 20 million particles, ladies and gentlemen, on my GeForce GTX 170, which is indeed a very powerful graphic card, but we should be able to go to 1 million particles, which is a lot of particles, even in graphic cards that are not so powerful. And on more powerful graphic card we will be able to go much higher. So that's it. This is what we are going to create using the new GL3 package. A bit forward, in order to use the GL3 package you have to go here into the preferences of Max and set OpenGL Engine to GL3, and then you have to restart Max. First, of course, you have to download the package from the package manager if you don't have it yet. Alright, okay, so now that we are ready to start, let's start. I will stop this here, put it in my other screen, so I'm not completely lost. Alright, so let's start. Let's first create a new patch. Let's save it. Let's call this GPU Particles Tutorial GL3. Okay. First of all, I will take my JIT-world object, which is a little snippet that I have. It's basically just a JIT-world plus a camera. I had to change the name because I already have a game and context called game. So I will call this GPU, and I will call also this GPU, and get attribute sites. This we don't need. Okay, very good. So we have our JIT-world. Camera to move around, and maybe we can set the position of the window when it first appears to 900, because to some of you I got the problem that then the window was completely outside of the screen because the resolution of the screen was less than Full HD, so there was no window. So in order to solve this, you just have to set the window position to something smaller on the x-axis. Very well, let's go on. So the first thing we need is, let's kind of create a skeleton of what we are going to use. We are going to use the new object called JIT-GL transform feedback. Now the transform feedback object, it works like this. It takes as inputs some GGL buffer objects. So first we have to say how many of these you need. And let's say we need 3 of those, okay? And then it gets the name of a shader that we are going to use in order to move our particles and display them. So let's give it the name of a shader, and let's call it my shader, for example. Okay, now let's create the GGL buffer objects. So GGL buffer, and the GGL buffer, it needs an attribute called type, which basically means which kind of buffer of the GGL mesh object this is going to replace, because the GGL mesh objects take some inputs, right? Let's actually take a look at it. It takes some inputs like position, text card, normals, color, specular array, and so on, right? So these buffers that we are creating are going to replace those buffers inside the GGL mesh. Now they are called array here, matrices, but they're actually buffers inside the GPU for the GGL mesh object. Okay, So we have to give this a type that is going to match with a type of the GGL mesh buffers, internal buffers, and is going to replace it. So we can choose, for example, position. So this is going to replace the position buffer. And this is actually very important that we choose position, because this means that we are going to update the position of the vertices of the GGL mesh. Okay. Then we need also an out name, and we will see what an out name is later for this buffer. So let's call it, for example, O position, which means output position. Okay, let's connect this here. Now we need another GGL buffer. Let's create another one. And this is going to replace the normal buffer, the second one. And this doesn't really matter, the third one. This doesn't really matter which buffer we are going to replace with this, because this is going to be our velocity. So the velocity of the particles that we have to store every frame, and we have to pass to the sequent frame, we have to store it in a buffer. So we're going to use the normal buffer to store these, even though we could use actually every other one. And then we have to create another one. We want to create another one, which will be the color buffers. So let's say color, output color, and let's say type color. So we're going to replace the color buffer of the GGL mesh, and we are going to use, kind of modify the color of the vertices of the GGL mesh using our buffer. Okay. So let's give also a couple of attributes to our GGL mesh. Let's say draw mod points, because we want to create particles. So they are like vertices represented as points. Then what do we have? Color, okay, we can set it by default to 1. Yeah, let's actually, for the moment, let's just leave it like that. Okay, now let's see how actually let's color all these 4 fellas with a single color. Just remember that these are kind of special objects. Oh, this card is really ugly. Okay. So let's now see how this is going to work. So we are going to fill these buffers with some matrices in the beginning, just at load bank. Okay, and then these matrices, these buffers at every frame, they are going to be updated with the result that we are going to output from within our shader, and they are going to pass the new position, for example, to the next frame. Okay, this is how the transform feedback works. So feedback, because we fill these buffers with some values inside the shader, and then they're going to basically to be fed inside themselves again. Okay, maybe it's a bit confusing, but let's see how this works in practice. So first of all, we need some default some starting values. So for example, let's say we want 100,000 particles. So 100,000, or let's say 500,000. Why not? Since we already proved that this works with 20 million particles. So let's connect this here. JIT noise. So some random values. We don't want these values to go from 0 to 1. We want them to go from -1 to 1. So we can use, for example, JIT map, and then let's say map 0, 1 to minus, let's say 0.9, 0.9. Okay, so let's connect this here. Let's create a bang. Let's actually create a load bang. Okay. And now we need some other JIT noises. So let's do like this. This will be it's going to fill our initial velocity. So let's maybe want to fill our initial velocity from 0 to 0.00, let's say -0001 to 0.01. This will be our initial velocity. And then we need to have the color, which is going just to be, for the moment, just to be a JIT noise with four values. Okay, let's connect these to trigger bang bang bang. So load bang, this, and that. Let's also connect a bang just to bang these out. And cool. Okay, we can already see that we got 500,000 particles on our screen in the range minus 0.9, 0.9. Why 0.9? This is we're going to see later. Actually, it doesn't matter. We could also say minus 1. Okay, exactly. I'm able to move around with the camera because I have this Gitanim drive, which allows us to move using WASD. Okay, cool. Okay, now let's go to the meat of it. So let's create actually a GGL shader object. GGL shader, where is it? Up there, GPU. Let's give it a name. So name my shader, and let's give it also a file name. File GPU particles tut.jxs, which doesn't exist yet. So we're going to create it. Now we double click on it, we get the default shader. So let's actually save it. I saved this on the desktop, so I will save also the shader on the desktop. So particles tut.jxs. I think this is how I named it here, right? Okay, so it should be here. There it is. Okay, so cool. Now let's actually give it let's actually send it a message. Read this file. So we are going to edit the shader using an external editor, like I think we're going to use Visual Studio Code. Let's actually open it. Oh, this is the shader that we're going to create, but let's create it from scratch. So let's actually go here, import is here, and right. So this is it. Let's choose the syntax. It's going to be GLSL. Plain text, no, GLSL. Alright, so this is the default shader. Okay, this is the default shader that we have when we create a new GGL shader object. Okay, now let's give it the message read the shader and compile it, so we can change it from here and then get it updated inside our shader inside Max. Okay, let's start. First of all, by default, we will have a geometry shader, which we don't need it. We don't need it at all. So let's actually just delete it. Let's get everything that is a bit after the. Let's get everything that is after the vertex shader and before the fragment shader, and let's delete it. Okay, the geometry shader, we don't need it for a particle system. So let's just delete it. Now you can see the syntax. It's a bit different from the syntax from GLSL 1.2. This is GLSL 3.3, which it's kind of very different. So let's see what we actually need. We actually don't need the model view projection matrix, because we are going already to we are not really rendering the vertices of the object. We are just using the shader. This is a bit tricky. So we will use the model view projection matrix if we were attaching a shader directly to the GGL mesh, because this will mean that we are going to transform the vertices from world space into cameras, into screen space. But this we actually are not doing inside the transform feedback. We are just going to use the shaders to modify the position of the vertices. So it's not like this is a shader that is actually rendering the object. It's just used to modify these buffers. Okay, so this is why we don't need to update the GGL position. We don't need to update the GTout color. Okay, this is all stuff that we don't need to do it here. We can also actually delete this struct that goes out because we are not going to use it. And okay, let's actually see what we are going to use. So we need the position and the color buffers that we declared outside. So basically, this position and this color refers to these two names, type position and type color, that we declared inside Max. Okay, so this is very important. This must be taken from the state position and state color. This, as you can see, is a vec3 because we fed it with JIT noise with 3 planes. And this is a vec4 because the color has 4 As for numbers, the position is 3 numbers because x, y, and z. And language name GLSL, blah blah blah. Everything looks good. Now, let's actually not call this simply position, but let's call it I position, which stays for input position. Because this is actually what we get as an input. Okay? This is the input from the previous frame that we get inside. So the buffer, it goes inside, gets modified, and gets output again inside the buffer. Okay, you have to imagine. So this is our input. So let's modify the name also here. iColor. We don't need a model view projection matrix as said. Ciao. Okay, cool. Then we have also another one, which is the velocity. So let's create another parameter name input velocity. So I velocity, and this we say is the normal. So type state normal. Okay. Let's create another one of those also because we have to bind it to the vertex shader. So I velocity. Well, cool. That's it for the moment. Now let's go actually here. So let's create another input back 3 I velocity. So the input means this is the stuff we are getting inside the shader. All right. Now we also have to output stuff because the stuff the output must go to fill these GGL buffer objects, right? That we created because it must be a feedback chain. So we have to input them, modify them, and then output them. So let's create some outs. Output back 3 position, right? Output back 3 velocity, which is, by the way, the name we gave to these buffers, right? Velocity, position, and color. So out back for color, right? Let's maybe put also the velocity after the position. Doesn't really matter, but just to be super precise. All right, now here in the main function, let's see what we need to do. First of all, let's simply modify the position by adding the velocity to the position. So let's do like this. Out position equal to the input position plus the velocity. So the input velocity. Okay, so I'm saving this here. Oh, actually also in the fragment shader this we can delete because we don't need this stuff actually at all. Okay, so I created this little line, output position equal input position plus the input velocity, right? So we are going to update the position by summing it to the velocity. And then we need to set the enable parameter of the GGL transform feedback to 1. So let's create a toggle in order to activate the feedback. Let's actually first read again the shader just to be sure that it was actually read. Did it actually work? Yes. Okay, so let's enable it. There is a problem. Okay, cool, there is a problem. Let's see what we got. Shader error in program. Link info. Name velocity specified but not present. Okay. So let's see what we did wrong. Oh yeah, right. So we actually need to specify all the inputs and the outputs. So the error was because I declared all velocity and all color, but I never assigned them. So let's do this. All velocity, let's simply assign this to input velocity. Okay. And then all color, let's simply assign it to input color. Okay. Let's see if it still complains. Let's read the shader. Let's enable the transform. Oh, okay, it's working. So you can see. Oh, and by the way, when you go full screen, it's just going to stop the transform feedback. We can kind of solve this problem in a couple of ways. We are going to do like this. Let's create a key object. Let's say select 32. And when we get 32, it will just output a 1. So every time we press the space bar, it's going to enable again the transform feedback. Let's put this inside the subpatcher, and let's do like that. So every time I press the space bar, it's going to enable the transform feedback. So as you can see, it's simply summing the position of the particles to the initial random velocity. Pretty cool, right? It's already working. By the way, every time you go full screen, at least on Windows, you get an error on the console. Just ignore it. It's a bug and is already being pointed out to Second74. They are working on it day and night. So let's see what we have to do now. Okay, let's make it now a bit more interesting. Let's create now a target that these particles are going to be attracted or repelled. Now, what I did in my example is that I took a GTBFG function and used it as a way to extract a random position on the world's kind of smoothing moving position inside our virtual world. So let's do it. What we are going to need is, actually let's create a subpatch target. Let's call it target. Okay, inside here what we are going to need is a GBFG object, not a GGL BFG. Doesn't matter that it's not, it's actually better not to make it GPU related, because we are just going to use, we're going to use this to extract 3 single numbers, so it doesn't really matter. It's actually better that it's not GPU related. So GTBFG, 3 planes, because we need 3 numbers, float32, 2, 2, 1. It could be actually 1, 1, 1, but GBFG, it doesn't work if it doesn't have at least 2 dimensions, so 2 cells on the first and the second dimension. Okay, this is why we say 2 and 2. Cool, then let's choose a basis. I will say noise simplex will suit our needs pretty well. That's it. Let's then create a receiver for our metro that we send from the world. So every frame we get a bang. And let's attach this to a counter. Okay, so we produce numbers continuously advancing. Let's divide this by 200, for example. So we get a continuously advancing number. And let's attach this to the offset. So 0 for the first dimension, 0 for the offset of the third or the second dimension. We are going to affect the offset of the third dimension, okay, which is just a 1. And let's see what we get when we do this. We get simply some noise. Oh, of course, I need also to send a bang to the GBFG. Right. So this is what we are getting out. And with this, we can actually transform this into a list of numbers by using JIT-iter. So let's see. But first, we want actually to get only one single list, because JIT-iter is actually going to print for every frame. So let's actually detach it. For every frame, it's going to give us actually 2 lists. Oh, actually 4 lists, because it's 2 by 2. So we are going to get 4 lists. 3 here, 3 here, 3 here, and 3 here. So we actually first want to get a single, just a single cell. So let's do like that. Float32, size 1, adapt 0. So we are just going to get just one single of those cells. Boom, we get just a single. We get just a single cell from these 4. Okay, very well. Let's detach the print. Cool. What we want to do now, before we transform this simply into a list of numbers, we want to go with GGen. What we want to do is to normalize those numbers so they just go between -1 and 1. Okay. We are not using the normalize object JIT normalize, because it just makes them go to -1 to 0, from 0 to 1. We use the normalize inside GGen. Okay, very well. Now this is going to be the position of our target. So let's actually create a GGL grid shape. GPU shape sphere scale 0.02, let's say. And this is going to be kind of the visualization of our target that our particles are going to follow or to be repelled from. So let's see, let's make him maybe a bit more big, and that's it. Let's say prepend position here, from here to that. Okay. Now let's actually restart again. Let's take a look. Here is our target going around in the world, right? It goes fairly fast. That's because we set here 200. If we say like 400 is going to go slower, but I kind of like that it goes pretty fast. So let's actually also say prepend u target. Now let's actually say prepend param u target. So this is going to go inside the shader. Okay, so let's create an outlet. Okay, so this is going to go inside our shader. Now let's go inside our shader. And let's create this uniform parameter. So param name u target. I say u because this is a uniform parameter. So I use this convention of putting a u in front of the name. Type, this is a vec3 because it's a position in a three-dimensional space. This is not a state parameter. This is simply a normal uniform. So we're going to say default. We're going to give it a default value, which let's say is the center. And then let's close this. Okay, let's create another binding. And let's say u target. Very well. Now we can use this parameter inside our shader. Let's first declare it, uniform vec3 u target. And okay, so now what we want to do is to create a vector that we can use to make our particles go in the direction of this new target. Okay, so in order to do this, let's go here. Let's create a vec3. Let me make this a bit bigger, right? Let's create a vec3, let's call it direction, and this is going to be the target minus the input position. So this is going to be a vector that goes from every particle to the target. Okay, every particle is going to have its own vector that goes to the particle itself, to this target. Okay? Okay, then let's create, let's normalize this. So norm dir equal normalize dir. Okay, because we just want this vector to be in the range 0 to 1, because we don't in this way it will be bigger, the vector, if the particle is farther. In this way they're all the same size, so we can then multiply it again for some value, and it's much easier to control. Okay, so let's get also the parameter of the distance from the particle to the target, and we can do this by using the length of dir of our direction, because this is exactly a number that tells us how far the particle from the target. Now let's create our acceleration. So this is going to be a vector that is added to our velocity every frame, and which accelerates the particles in the direction of the vector. So let's say this is going to be our normalized direction by multiplied by some value. Let's say 0.01 just to start. Let's say maybe 0.01. Okay. So this vector is going to be our acceleration vertical is going to be of magnitude 0.01, because we first normalized it and then multiplied by 0.01, so the magnitude is going to be 0.01. Now let's actually make the acceleration related to the distance. So we have to divide the acceleration for, let's say, the distance multiplied by some number. For example, I multiplied by 50 squared, so this by the distance multiplied by 50 plus 1, just to not divide it by 0, because if the particle is too close to the target, so it's actually a difference of 0 between the particle, the distance of 0 between the particle and the target, we will be dividing by 0, and this we don't like, because then it will be a much too big number. If we divide something by something very close to 0, we will get a super big number, which we don't want. So we add 1 in order to prevent this. Okay, now what we have to do is to basically assign velocity 1, so output velocity, sorry, to be equal to I velocity, so the input velocity, plus the acceleration. Super easy. So we can actually delete this here. Let's also multiply our output velocity for some number less than 1 in order that every frame is kind of, the velocity is a bit dampened out, okay? So let's multiply, for example, by 0.98. Okay, and now let's clamp this velocity between Mamma! Sorry. So I was saying, let's clamp this velocity, doing it like this. So out velocity equals, we're going to clamp it in order that the velocity doesn't get greater than a certain amount, because otherwise it will, if we didn't dump it, it will just get bigger and bigger. So we can actually even dump it, but also clamp it in between two values, so it doesn't go above those values. So let's do like this. Clamp, it's a built-in function of GLSL, so O velocity, and let's clamp this using vec 3, and let's say minus 0.04, and vec 3 0.04. Okay, so this looks good. Then again, let's say O position equal to input position plus O velocity. Okay, and for the moment this should be it. Let's try. Okay, let's activate it. Alright, so as you can see, the particles are attracted to the target. Now maybe okay, let's do like this. We can use some fixed numbers, but as you can see, now I want, for example, to modify this number. Then I go here, reload the shader, and then I go that, and it's not so cool to always go inside the shader to change those values. So we can actually create some uniform in order to basically we can actually use some uniforms in order to modify those values from outside the shader, so from the patch, like we did basically for the U target. So let's do like this. Let's actually copy the U target, and let's create another U called U max vel, and this is also going actually to be a float, and let's say a default value of 0.04, right? This is what we were using. Okay, then we have to assign it, to bind it like this, and then we can declare it here, uniform float, it's called max vel, and then we can actually just use it inside our shader. So let's replace those two numbers with it. Cool, let's also create one for the dumping, so let's call it dump, and let's say by default 0.987 or something like that. These values you can also always modify and see what works better for your particular aesthetical needs. Okay, so dump. Let's go here and let's replace this with dump. Okay, so we can go now outside and we can say param dump $1 here. Then we can say param max vel max vel. Okay, now we can use some floats to modify this. Let's actually create another parameter for the strength of the force. So this number here is 0.01. So let's call this U force amount. Let's give it a default value of 0.02. Let's create also the binding. So okay, this is going to be also a float. uniform float force amount. Let's use it here. Okay. So let's go here. Let's create another one. Force amount. Okay. So let's try again. Let's augment, for example, the force amount. And let's see what's happening. Okay. Now it's starting to look fairly cool. Right. Now, what we could do, for example, is to modify the color of the particles. Oh, and also what we can do is to assign a different mass to every single particle, so they will all have a different velocity. Also, if they are the same distance from the target, they will anyway have a different velocity. Okay? But first, let's actually play a bit with the appearance of the particles. So we can say we can enable the blend for the mesh. I can say blend add. I can say depth enable 0. Okay, so now it could get a bit cooler, because the particles are going to when they are kind of close together, they are going to be brighter. Okay, so this already looks cool, I have to say. Right, so let's modify the color of the particles. So let's go here. Instead of assigning simply the output color equal to the input color, what we can do is to actually just create a color of our choice. Let's say this blue color that I used in my example, which we can also, by the way, modify with a uniform. I think we are going to do that later. And then let's multiply that by the length of the speed of the particle, so the length of output velocity, multiplied by some big number, for example 30, and then let's add to this like a small number in order to not let the particles ever be black. Okay, so let's see, let's read the shader, and right, we're getting close to the appearance in my example video. Okay, still pretty dark. Maybe we could set the size of the point to 2. So let's do like this, point size 2. Let's see what we get. Okay, I actually prefer when it was 1. Right, we can maybe multiply this by some bigger number. So instead of 30, we can also set this to a uniform, as you probably already got. And right. Okay, very cool. Now that we are not using the input color for anything else, we can actually use it as a mass. So we can do like this. We can multiply our normalized direction by the attraction amount, and then we can divide it. Sorry. We can divide our acceleration by our mass. So let's do like this. Let's say iColor.x, for example. Okay. Oh, and so now every particle has a different acceleration, so a different velocity. Okay. And this is fairly cool. But since the noise is only between 1 and 0, we're actually when dividing, we're actually multiplying. So we can go here with a JIT-gen. And depending on what you want to achieve, we can multiply this by 2 and add maybe 0.5 in order to never divide by 0. Let's load bang again, and yeah, starting to be quite cool, because now every particle has a different mass. Just one more step and then we are done. The one more step is to basically to make in a way that the particles, when they go outside of an area that we choose, they reappear from the other side. So we just rewrap them. In order to do this, we can do like that. We can use the modulo value. So after the position has been assigned, added to the velocity, we can do like this: O position. And this I have to copy from before because I don't remember exactly how I did. Okay, so this is going to be output position plus. Let's say that we want our world to be in boundaries between -2 and 2. Okay. So what we want to do? The position we want to basically we want to scale it between 0 and the maximum amount that we want. So since we want to go between 0 and 2, we actually just going to add 1. So O position back 3. This is the modulo of what we want to get. And then we subtract half of our modulo, so vec3 2.0 to that. So let's see if this is actually correct. No, this is not correct. Maybe like this. Yes, so I had to add 2, because then they go from 0 to... no, then they go from 2... from 0 to 4, because normally they can go from 0 to 2, from -2 to 2, plus 2, they go from 0 to 4, right, it makes sense. So this is just the wrap position. Okay, we are done. Ladies and gentlemen, we are done. You get our particle system. Now you can see when the particles go outside of this cube, they basically go inside from the other side, and all this stuff we can, all the parameters that we actually hard coded, we can actually set them as uniform. This I maybe leave to you as an exercise. Plus we can change those parameters in order to completely change the behavior of the particles. I will say this is extremely cool. This opens up so many possibilities. I'm really happy about the GL3 package. It's great, and I cannot wait to work with it a lot. So everybody, thank you very much for following me through this little journey. And if you liked it, you can consider to support me on Patreon. First of all, to download this patch, and to download millions of other patches. Not millions, but hundreds, maybe thousands of other patches. No, I don't think thousands. Definitely hundreds of other patches, and you will support these tutorials. So, thank you very much again. See you in the next video. Ciao.